All right, this is CS50, and this is first year family weekend here at Harvard. So welcome to all of the moms and dads, brothers, sisters, cousins, aunts, uncles, grandparents, and beyond. CS50 here is Harvard University's introduction to the intellectual enterprises of computer science and the art of programming. And what that means is that what we've been doing in here over the past several weeks is introducing students to computational thinking, the process of cleaning up one's thoughts and expressing oneself all the more correctly, all the more precisely, and ultimately translating those thoughts, of course, to a computer in the form of programming, which is where we've spent quite a bit of time programming, writing code over the past several weeks. But toward that end, we've also been equipping students with some basic building blocks. You might already know, if a parent, that computers only somehow speak zeros and ones, even if you're not necessarily a computer person yourself or know what that means. But with those zeros and ones, can we represent numbers and letters and colors and videos and more? And in fact, your child, perhaps sitting next to you, could perhaps tell you what today's message says. Here we have 64 light bulbs on stage, and if you look at 8 of them at a time, there's a pattern of bulbs that are either on or off that, if you know the code, so to speak, can you actually convert these bits, these zeros and ones in light bulb form, to today's particular message. Now, before we begin, we thought we'd make this as engaging, as interactive as possible. Rather than focus on any assumptions of prior computing knowledge, you need know nothing today other than how to operate, for instance, your own phone or a laptop or desktop or the like. And indeed, we'll assume a general audience. And in this Halloween week, we also see if we can't scare you a little bit into practicing better practices when it comes specifically to the security or cybersecurity of the device you carry with you every day in your pocket, use on your desk, on your laptop, or beyond. So if you haven't already, whether you're here in person or tuning in online, go to this URL here, which will lead you to an interactive polling tool. Any phone or laptop or desktop suffices. If it's a little easier than typing in this URL, you can just scan this code with your phone's camera. Take a moment to just open your camera, and hopefully, if you're at a good enough angle and we've made this thing big enough, this is a 2-dimensional barcode or QR code embedded in which is that exact same URL. We're increasingly seeing this throughout the world as a mechanism for doing what many of you are doing right now, linking the physical world to the virtual. But that URL, again, is simply this one here. And in a moment, you'll see on your screen, it's OK if you weren't quite able to get that working. Feel free to glance to the left or to the right of you for someone else who did. Let me go ahead and full screen a question just to ask of everyone here as we focus today on cybersecurity. Is your phone secure? Whether an Android phone, an iPhone, or anything else, if you're holding it in your hand right now, here in person or online, you should see 3 possible answers: yes or no or unsure. We've got over 300 responses come in already. In a moment, I'll flip over and reveal the results and see if we can't see how much work we have to do together here today. A few more seconds, almost up to 400 answers. Almost up to 400. It's OK if those keep coming in. I'm going to toggle back and show the results in just a moment here. And the results are now in. According to a response rate of over 400, it looks like 36% of you don't need what we're about to do here today, which is great. We'll see if we can't poke some holes, though, and maybe some assumptions you all are making. 31%, 32% maybe of you are a little are saying, no, your phone is not secure. So glad you came. And then understandably, to another third of you are unsure. So in very good company today. And we'll see if we can't open the eyes of everyone in each of these disparate audiences. Well, let's consider first for a moment exactly how we might think about the security of our phones, representative of just any computing device. And in fact, everything we discussed today could be extrapolated to laptops and desktops and servers. But all of us being so familiar with phones, let's start with phones themselves. Now, odds are you have on your phone, like so many other things in your life, a password or a passcode. And in fact, without raising your hands and therefore leaking information, think to yourself, well, what is my password or passcode? It's probably 4 digits. It's maybe 4 letters. Maybe it's even longer. Maybe it's even nothing. And I think maybe from the chart earlier, we can assume that we have a third of each of those possible responses. So a password, of course, is this super common mechanism that you and I are all using all the time to keep our devices secure. But do passwords keep things secure? Like, how many of you thinking about your phone right now and that specific password might think it's secure? And if so, why do you think it's secure? We have at least 33% of you are ready to say that your password's secure. Don't want to know it, but why might it be, in your mind, secure? Why might you think it's secure? Or more generally, what makes your password secure? It's random. OK, so it's random, so random letters and numbers and the like. And that's great because it's not just a word in the dictionary that someone could guess and type in. Downside, of course, I dare say, is that it might take you, as well as anyone else, quite a bit of time to guess or figure out what, or just to remember what it is if it was indeed random. But randomness is going to be a primitive that really actually helps us. Unfortunately, you and I and really the whole world are not very good even at passwords, as omnipresent as they are as a defense against adversaries. In fact, if we look at the most common passwords from the past year in 2020, thought we'd share with you some of those results. This is the result of security researchers having found big exploited, compromised databases, analyzing them for what passwords are in them, and then inferring from that what the most common passwords you and I are all using. Unfortunately, in 2020, the most common password, according to one measure, was 1234566. Now, funny, yes, but if you're seeing your password on the screen already, not so funny, perhaps. The number 2 password was not much better. Number 3, picture 1, presumably for a device, a website that requires that it not just be a word, it have at least one number, which this person took literally, these hundreds of thousands of people took literally. Password was number 4 this past year. 1, 2, 3, 4, 5, 6, 7, 8. 111, 111, really not trying hard there. 123, 123, varying it a little bit. 1, 2, 3, 4, 5 was number 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 was number 9. And then number 10 in 2020 was senha, which, any Portuguese speakers here, means password, means password. So made the list twice in this case. So one takeaway already today should be if your password's on this list, like, probably you're in one of those other 33% whereby we can do better than this. Why? I mean, really the obvious. If you're in this list, there's so many bad guys, so to speak, out there that are going to try guessing your password first. Why? Because just statistically, if they try 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, they're just going to get into a lot of devices quickly because they're just so commonly used, those passwords. You don't want to be on this list. Ideally, you want to be random, but we want to somehow balance randomness with memorability so that you don't actually keep forgetting your password, which of course defeats the whole point of these things in the first place. But in a class like this, CS50, and computer science more generally, let's be a little more thoughtful as to what we mean by a device being secure. Like, what does it mean to be secure? And can we even slap some numbers on it so that we can make measurements, so that we can ideally compare and contrast one system versus another, one password versus another. So it's not just our instincts arguing that my password is better than these, but how can you quantify that perhaps? Well, let's start simply. A lot of Android phones and iPhones these days require minimally that you have like a 4-digit passcode. You're minimally encouraged to have at least this bar set so that you're not having no passcode altogether. So if you do have a 4-digit passcode, well, let me go ahead and ask this question. How much time might it take to go about cracking, so to speak, that is figuring out what a 4-digit passcode is? In fact, let me go ahead. If you want to pull up your devices again, you should see on the screen this question now. How long might it take to crack, that is figure out, guess, a 4-digit passcode, for instance, on someone's phone? A few seconds, a few minutes, a few hours, a few days. Thinking here from the adversarial perspective, if someone got a hold of your phone somehow, how long do they need to get into your phone if it has a 4-digit passcode? A few seconds, few minutes, few hours, few days. Got about 300 responses so far. Let's give folks another few seconds here. Another few seconds here. All right, up to 350 or so. In a moment, let me go ahead and flip screens over to the results. So we'll see the preliminary results here. And if I now pull this screen up, we see that 50% of you claim that it's going to take only a few seconds. Few of you say, about a few fewer of you are saying that it takes a few minutes, a few hours, and even a few days. Well, let's answer that first, because honestly, if it's already a few days or even longer, our work is here probably already pretty done. Unfortunately, the problem with things like 4-digit passcodes is that anyone who grabs your phone, you step out of the room, you leave it behind, you lose it, they could certainly mimic your input device and just use their finger pretending to be you, trying 0000, Nope. 0001. Nope. 0002. Nope. And it's a little slow, to be fair. It would take me a while to count all the way up to 9,999. That's 10,000 total possibilities there. But let's go ahead and consider exactly how else you could do it. For instance, here is an example of, in computer science, what we call a brute force attack. And just an adversary using their finger is a brute force attack if they're trying all possible passcodes. The problem is, even if your passcode is way at the end of the list of numbers, eventually they're going to get it by brute force. Sort of like in yesteryear using a battering ram or the like to brute force your way into a building, a castle or the like. In software sense, it just means trying all possibilities. And you don't even have to just use your finger, right? Anyone with some programming savvy who's good with hardware could maybe do something like this. Here's a quick video I'll hit play on. No sound, but a little bit of a robot that has an Android phone underneath it, and it's got a little robotic finger that's doing the work for you. You can step out of the room now as the adversary, let the robot do its work, trying 0000 through 9999, and ultimately, presumably, get into that phone. So let's see if we can't quantify then exactly how fast the human or the robot could get in. Well, how many total possibilities are there? That's the right way to begin thinking about it. If you have 10 digits for the first one, 0 through 9, and then another 10 possibilities, another 10, another 10, the total number of possibilities, of course, between 0000 and 9999 is 10,000. 10 times 10 times 10 times 10, which gives us that much of a search space, a universe of possible passcodes to choose among. Unfortunately, you can do even better than your own finger or even that robot. Anyone in CS50 now who knows a bit of programming in languages called C or Python or anything else could open up a programming window and actually just start writing some code. And so let me do that. What you're seeing here, if a family member, is a programming environment called Visual Studio Code that students have been using for the past several weeks. Up here, we have a tabbed window where we can type our code. Down here, we have what's called a terminal window where I can type commands to make the computer run that code. And then over here is just a menu bar. So crack.py means I'm going to write a program to crack, that is, figure out passwords using this language called Python. And even though most CS50 students wouldn't know what code to start writing, they'd have to look up some of what I'm about to do. It's only going to be a few lines. So I'm going to go up here and say, from string import digits. This is a fancy way of saying, hey, Python, give me access to all decimal digits. It just avoids my having to type out 0 through 9 manually. All right, then I'm going to say from iter tools, import product. This is another feature of Python that CS50 students, for the most part, have not yet seen, that just says, hey, Python, give me the ability to do like the cross product of a whole bunch of numbers. So these 10 times these 10 times these 10 times these 10. And then what am I going to do with that? Well, for each possible passcode in the product of those digits repeated 4 times, I'm going to go ahead and, for now, let's just print out what the passcode is. In other words, assume that I am now the adversary. I don't want to waste time using my finger. I don't have a robot that I made. But I am good at writing software. And heck, I've got like a USB or a lightning cable in my bag that I could connect your phone to, my Mac or PC. And I could just have my code that I'm writing now send all the possible codes from laptop to phone to automate this process just using the little port at the bottom of all of our phones. Well, let me go ahead and maximize this so-called terminal window, which is, again, where I'm going to run this code. And again, the question a moment ago was, does it take seconds, minutes, hours, days? Well, let me go ahead and run Python of crack.py. I'm pretending for the moment that I did grab that cable from my bag and plug it into the phone, hitting enter, and it didn't actually do anything. That was not supposed to happen. So in CS50, we spend a lot of time introducing students to bugs, which are mistakes in programs, sometimes not so deliberate. Let me go ahead and apologize. Let me open this file. This didn't technically happen. OK, Python. There we go. OK. In CS50, we now will run the code here. And I'm going to go ahead and run a command called python of crack.py. I had the file in the wrong location a moment ago. And this is the equivalent on a Mac or PC of double-clicking an icon. Here we go. Is it seconds, minutes, hours, or days? Barely 1 second to try all 10,000 possibilities. You can't even see them all on the screen, but this printed out 0000 all the way down, of course, to 9999. Plug in that cable, and boom, the adversary doesn't need to be in that room for very long in order to get into that that phone. All right, so what would be better then? Like, clearly, 4-digit passcodes, bad if you have someone in your life who has a finger or a robot or the ability to write code. And unfortunately, because of us, you now all have someone in the family with at least a third of those. How might we do better than this? What's better than a 4-digit passcode? Anyone? Yeah. OK, so 6 digits, heck, or 7 digits, or 8 digits. Why? Because that's going to make, of course, the passcode longer, which means we're going to have to try more possibilities, which doesn't mean that the adversary is fundamentally stopped, but it is going to slow them down. It's going to take them more time, probabilistically, to get to your passcode. And it, in a sense, then increases the cost to the adversary. And indeed, that's the theme in cybersecurity, raising the cost to the adversary, either financially or time-wise or the like. Just like in the real physical world. Most of you go home. You lock your doors at night. You might have invested in a better deadbolt than another. Why is that? You really just want to be more secure than the house next door. You want to make sure that it takes too much time, too much effort, too much risk to the adversary to get into your home. And that's, again, what cybersecurity is all about. To say my phone is secure is sort of nonsensical. To say that your phone is more secure than someone else's, that's really a reasonable, fair statement to make. So I like this instinct. Let's see if we can't make things a little harder. And actually, let's go one step further. Rather than just numbers, you've probably noticed on your phones, you can use letters of the alphabet too. If you click the right option on the phone, you can start typing in words and letters. So how might we do that instead? Well, let's transition to 4-letter passcodes. 4-letter passcodes. And if we do 4-letter passcodes, where the letters of the alphabet, for instance, are A through Z in English alone, let's go ahead and ask this question here. If you have 4 letters of the alphabet, so let's not increase length yet. Let's just change to a bigger vocabulary. Now we have A through Z instead of 0 through 9. How many 4-letter passcodes are possible? How big is that universe that the adversary is going to have to search via brute force? So I'm seeing a lot of 7 millions, a bunch of 52,000s, 26,000s, 10,000s, 9999, a few smaller numbers here. Hopefully it's not this low, right? Because we've already set the bar at 10,000 possibilities for numbers alone. Hopefully if we've got English letters, A through Z, we can at least do better than 10,000. So I think we'll start to see maybe some of these bars change a little bit. But we've got 60% of you proposing 7 million. Well, let's go to the math. So here we might have a way of thinking about this, both uppercase and lowercase, even better if you consider it that way. Lowercase A through Z, uppercase A through Z. That's 52 possibilities for the first digit, times 52, times 52, times 52, or 52 to the 4th power. That indeed gives you 7 million plus possibilities. All right, well, let's now translate this to code. That already sounds way better. 10,000 versus 7 million. This is definitely going to slow that hacker down. Well, let's consider exactly how fast or slow it might now be. Let me go into my crack.py program, and let me make a little tweak so that instead of just using digits, this time I'm going to use letters, otherwise known as ASCII letters, as CS50 students will know. That just means familiar English letters of the alphabet. And I'm going to change my code to use these ASCII letters, 4 of them still, instead of digits alone. And that's the only change. Now I'm going to pretend to plug my phone that I just stole from someone into a USB or a lightning cable. Let me maximize my window just so we can see things a bit more. Let me run Python of crack.py now. And let's consider how long it takes to do 7 million possible codes. OK, slower. Slower. Can't dramatically just say in one breath that we're done. But we're already at the G's and then the H's. And it's kind of flying by. You know, this is where the adversary is probably getting nervous in the TV show or movie, right? Someone is tiptoeing around in the other room. You don't want them to come in. You only have this much time to crack the code. And we're at the R's, the S's, the T's, U's, V's. So, you know, this feels like, what, a minute or so? It's a good number of seconds, but it's still pretty brief. Certainly if someone has the ability to, now we got to do the capital letters too. Certainly if someone has the ability not to just secretly do it like in Hollywood in the next room, but just take it with them and do it over the course of a minute or two at home, this seems to be faster. This seems to be slower because we're trying so many more possibilities. But you know, if the adversary takes your phone, has it long enough, this doesn't feel like terribly long. So what might be better than this? Let's take it one step further. What might be better than 4 letters? What do most websites ask you to add to the mix? So special characters, right? And those things are darn annoying, right? Because sometimes they even tell you what letters, punctuation symbols you have to use, and then you type one and you realize, oh, it's not on the damn list. I mean, it's frustrating. Why? Well, it's going to raise the bar, though, to the adversary. And that's indeed going to be the goal here, again, just to increase the cost or time required for the adversary so that it doesn't finish like it did just now after a couple of minutes, but it's going to keep going and going, hopefully, such that they're going to lose interest in your phone and go try to crack into someone else's, presumably. So let's try this. Let me now go over to how about one other question here. And this question will now just be, let's go from 4 characters. How about let's take it one step further and mix the 2 ideas here. More digits and longer passcodes. How many 8-character passcodes are possible? And by character, as a CS50 student will know, I mean number or letter or punctuation symbol now. And there's like 32 or so standard punctuation symbols. So we're up to a good set of numbers now. How many 8-character passcodes do you think are possible? Million, billion, trillion, quadrillion, or quintillion? All of which, of course, are better than 10,000 possibilities. So we're in a whole different space now. Looks like these answers are coming in a little more slowly, perhaps as folks think about this. This is 10 digits plus 52 letters plus 32 punctuation symbols. Much more secure, it would seem. All right, we're up to 230 responses. Give folks another second or so. If you're trying to do the math, 10 plus 52 plus 32, that's going to give you 94 possibilities for each of the digits. All right, we're just about at our 350. All right, I'm going to toggle over the screen here. Going to click over to the results, show them in just a second on the screen now. And this is an interesting distribution. I think some of you perhaps have the instinct now of just go for the biggest one. It's not quintillion, nice as that would be. Maybe it's quadrillion, trillion, billion, or million. We have more of a split there. So let's consider the math. So if we've got 8 characters, and I claim that that's 94 possibilities for each, 10 digits, 52 letters, 32 punctuation symbols, that's 94 to the 8th power, essentially. And that indeed is 6 quadrillion possibilities. Now, that's crazy big at this point. I dare say we're pretty safe from the human finger now. We're probably pretty safe from that robot, which is going to take a while too. But Macs and PCs are pretty darn fast. And God forbid the adversary have a big server or use the cloud, so to speak, and really use a big, expensive machine. How long does it take to get into 6 quadrillion possible passcodes? Well, how might we think about this? Suppose, just for the sake of discussion, it takes the adversary 1 second per code, just so we have some unit of measure to start with. 1 second per code, which means in the worst case, the adversary really gets screwed, and my passcode is like 9999999, or with a lot of crazy punctuation symbols in it. If each passcode takes a second to guess, how long is it going to take the adversary? If in the worst case, they spend 6 quadrillion seconds. How many hours or minutes or days or years? I'm hearing a lot. A lot is, in fact, correct. I did do the math. The adversary, if they're lucky and get all this way, they're going to be 193,000 years old by the time they get to all of those possible passcodes. So this sounds alluring. And in fact, let's just change our code one final time just to get a sense of how this might look and behave. In this version here, let me go back into my code. And let me change this now to use not just ASCII letters, but digits. And I'm going to add in punctuation. For CS50 students, there is, again, this library called the string library that lets you just import all of these symbols automatically, so we don't have to type out every character on my keyboard manually. And then down here, I'm going to take the product of those ASCII letters again, plus those digits, plus the punctuation, repeated 8 times, I claim this time. I'm going to now increase the size of my window just so we can see more on the screen, rerun the code. And this is going to take us, some hundreds of thousands of years. So we won't run to the end of this demo. Now we seem to be in a better place. All right, so what's the takeaway here? Clearly, you should use a passcode, a password that's 8 characters with letters and numbers and punctuation. Yes? OK, so, there's a mix here. Some of you are saying yes, someone no. How about someone who says no? Why? Why no? Yeah. Recaptcha. OK, so there's other mechanisms. More on that in a second. Other instincts? Yeah.
Like the computers are much faster than just 1 code per second.
Yes, I'm kind of cheating with my verbal simplification here. Even this computer is way faster than 1 code per second. So it's not going to be hundreds of thousands of years. It might be tens of thousands of years or hundreds of years. But it's not going to be quite as dramatic as this. So that's a concern. Yes, so maybe there's other mechanisms. So maybe we don't have to be so extreme as to introduce all of this randomness as was proposed before. Because honestly, there's this theme in computer science too, and really information technology of trade-offs, right? Sure, I can use a really big random password, but my God, I'm going to end up writing it on my monitor on a Post-it note, which I suspect statistically some of you are guilty of, right? And you shouldn't necessarily just blame yourself or your colleague who's doing this. Like, this is a symptom, perhaps, of bad IT policy. If we don't have necessarily very usable systems, maybe we shouldn't blame the human for forgetting their very random password. Maybe we shouldn't require the human to have a very random password. So what could we do? A couple of technical mechanisms were just proposed. Let's go down this road of how we might try to defend against this. And I'll keep this running just for fun in the background. Let me switch back over to a visual here. Now that we've considered that many codes, what if we do something that some of your own phones already have that slow the adversary down? And some of you might have seen on your iPhone a screen like this. Let me zoom in. iPhone is disabled. Try again in 1 minute. Has anyone locked themselves out of their phone like this? I have. This is not, I mean, it's embarrassing to admit, but it's not leaking any information. All right, so many of you have done that already. But why is this actually a compelling feature? Just to be clear. Annoying as this might be, because you probably don't want your phone locked at the very moment you're trying to get into it, why might it be a good thing? Yeah, let's go somewhere else if we may. Yeah, I'm back. Sorry? It slows down the process. It annoys you, to be fair. Like, you pay a bit of this price, but it really slows down the adversary. Now they're going to be able to type in not 1 code per second, but 1 code per minute, a 60 times difference. That's really going to force them to pump the brakes. And unless that adversary is after you specifically, odds are they're going to go take someone else's phone or lose interest because you've raised the bar high enough to their getting in. On Android, if you do this, it depends on the operating system version. Here might be something similar on Android. Too many attempts, try again later. I mean, this is even more annoying. It doesn't even tell you when to try again later. But it does slow down the adversary. So if you don't have features like this enabled, you should. And if you're particularly security conscious or paranoid even, you can even enable a feature on these phones nowadays where they self-destruct, so to speak, after 10 wrong guesses. Right? Why 10? The presumption is among Apple and Google and others that if you type your passcode 10 times wrong, you're probably not who you say you are. You're probably someone else. Although, if you're a little groggy first thing in the morning, or if you've been out late and having a good time, 10 might not be a high enough threshold to sort of protect your phone from you. And so there, too, is this trade-off again. And that's an extreme one. If your phone deletes itself, which is what I meant by self-destruct, then that might actually be to your detriment, unless you have backups and all of that. But that's another technology question altogether. So there, too, this theme of trade-offs. You raise the bar to the adversary, but you've got to pay the price. You're not going to get any such feature for free. All right, what's another mechanism that many of us increasingly, thankfully, are doing? Might be when you log into a website like Gmail to have two-factor authentication, sometimes called two-step authentication. I mean, how many of you use two-factor or two-step authentication with at least one account? All right, so that's amazing. How many of you use it with all of your accounts? All right, fewer of us. And there, too, that's not necessarily the wrong answer, right? I have a lot of stupid websites that I have accounts on, like I bought something once on them. I don't really care about it. So there's a judgment call there in terms of what you really care about. But maybe your financial websites, your healthcare websites, or anything that's mildly sensitive to you probably should be raising the bar to the adversary by enabling this. So what is this? Particularly for those of you who didn't raise your hand, someone else, what is two-factor or two-step authentication? What's two-factor? Yeah.
When you have to use your phone to verify that it's really you.
Yeah, so when you have to pull out your phone and verify that it's really you, or in the corporate world, you might have a little dongle, a key fob on your keychain that's got a little number on it. But generally speaking, two-factor authentication is all about, indeed, a second factor. It's kind of oversimplified as two steps, but it's really key technologically that it be a different factor. It is not two-factor authentication if you just have two passwords that you have to remember, because both of those could be forgotten by you. Both of those could be stolen by someone else if you write them down, the Post-it note or the like. Two-factor authentication is about having a fundamentally different factor available to you so that the odds that someone get at something you know, like your password, and something you have, like your phone, is just much, much smaller than the threat of just figuring out something you know, like a password alone. So the factor is something that's fundamentally different from the other thing. And so once you configure this, the user typically sees a screen like this, for instance, in the context of Gmail. The screens vary here at Harvard and Yale. Students are familiar with something called Duo Mobile, which is the exact same idea. And they typically use one-time code, 6 digits thereabouts. And you can only use that code once. And the idea is it's texted to you or pushed to your device so that you and only you can use it. Does this fundamentally secure your account? Is this enough to just have a good password and two-factor authentication? Does that keep the adversaries out altogether? Not if someone, what? OK, not if someone really wants to get in. Then you have other problems that are certainly of concern. But you do want to ideally keep most adversaries at bay. And there, too, all we're doing is like raising the bar, right? There's nothing stopping someone in physical proximity to me stealing my phone and getting into all of those accounts I just raised my hand about. But you at least protect yourself against the billions of other potential adversaries in the world that are geographically not near us. So you at least narrow the threat. So that's a good thing. But what else could we do? Because I feel like it's not fair for us to say, all right, everyone go home, start using better passwords, longer, more complicated. Because again, there's this trade-off. We don't want to send everyone home essentially with a pad of Post-it notes to then counterbalance what's an unrealistic expectation. So how many of you, perhaps with a show of physical hands, use a password manager already? This is something practical we can equip you with. OK, so that was relatively few hands. And those of you who are in the habit still of memorizing your password, or worse, writing down the password, there are better solutions today. But here, too, there's going to be a caveat. There's no clear win necessarily. A password manager is a piece of software that you install on your Mac or PC or your phone that manages your passwords for you. And these come either built into the operating system. Windows has Credential Manager. Mac OS has something called Keychain. There's third-party software like 1Password or LastPass. Companies and universities often have site licenses so that students in particular can use these kinds of things for free. But the ones that come with your operating system or phone are themselves already free. And not using them is really the missed opportunity here. So what is a password manager? It's a program that, yes, manages your passwords, but it does a few things more. It generates passwords for you, typically. I mean, honestly, it's been years since I have chosen my own password on a website. I instead click a button in my password manager software, or I use a keyboard shortcut to generate something that's 8 characters, heck, maybe 16, 24, 32 characters long. I don't care, because the software's job is to manage that password for me. That is, the software remembers this crazy long password for me. And better yet, it comes with a button or a keyboard shortcut that will automatically fill out forms for me on the web. When I say log me in, it will grab my password from my computer, plug it in, and voila, I'm logged in. The upside of this is that even if that website is compromised and my password leaks out, I'm not using that password presumably anywhere else, because the software's job is generally to create unique passwords for each website. And it's not going to be guessed via brute force by one of you writing code, because it's just too long. Probabilistically, we're all going to be gone by the time your computer finishes trying to crack it. So what's the downside? I mean, this sounds great. If the software generates passcodes for you and plugs them in for you, where's the downside? Anyone? Yeah.
If you're using somebody else's computer and need to access it and you don't know the password.
Yeah, if you use someone else's computer, or you're in like a library environment, a lab environment, you don't have your passwords accessible. Now, there's a way to mitigate that so long as you sync the same software to your phone. You might have to pay another $1.99 or $20 to have the same software on your phone. You can at least mitigate that by sharing the passcodes across your devices. Not as user-friendly. You're still going to have to now manually type out this really long password. And that, too, is annoying if you get one character wrong. But that's one way to mitigate that. Other concerns? That's maybe the biggest threats. I mean, you're kind of putting all of your proverbial eggs in the same basket. If someone now gets into my password manager, which I should stipulate is supposed to itself have a really big, long password that I do have to remember, but only one such long password, I mean, then I'm really out of luck. Now, every single account I own is compromised, except for those that at least have two-factor, unless the adversary also steals my phone or my key fob. Other concerns? Exactly. If someone gets physical access to your device, honestly, in general, all bets are off. And this is why some of today's lessons are really important. It's only going to matter when you first lose your phone or someone walks off with your laptop or the like. There are certain things you can do to defend against that inevitability, dare say. But you want to make sure that if you are using some of these solutions like a password manager, that long primary password you use for it is itself really hard to guess. And I would say, I'm OK with you writing that down even, but putting it in like a safe deposit box or hiding it somewhere in the house that's just very low probability of someone finding. Because the other problem with putting all of your eggs in one basket, if you forget your password, then you lose everything. And that, too, seems like a pretty serious price to pay. But this is a constant battle in computing nowadays, usability and security and finding that inflection point. But there, too, you can be selective, right? I called out financial information, health information, your personal email, your calendar, anything that's mildly more sensitive to you or important. Raise the bar at least on those accounts, even if you're not quite ready to go all in on all of these other factors. Well, let's consider then where we're using these passwords. Consider just a couple of specific examples. Email, of course. Gmail is the example I used earlier. Gmail and email accounts more generally are increasingly offering us features. And in fact, there's one that I thought we could highlight as an example of something that, as a CS50 student, a CS50 family member, you should really start viewing the world with a more skeptical eye, a little more paranoid eye, and not necessarily just believe things that websites say. I mean, it's mostly meaningless when a website says, sometimes with a pretty little logo or emblem, our website is secure. Like, what does that even mean? And it's, again, all about relativity. And even Gmail, I dare say somewhat irresponsibly, has this feature in recent years, confidential mode. Like, is anyone, if you're using G Suite or Google Apps at work or Workspace nowadays, in the habit of using confidential mode? I mean, it sounds, OK, no one's using this, so this is great. And I worry now that I'm introducing you to a feature that you shouldn't necessarily use. But all this time, if you're a Gmail user, there is along the little menu bar an icon that lets you enable confidential mode. And later tonight, play around for it. Just look for it, and you'll see exactly the screenshot which I took yesterday. According to Google, recipients won't have the option to forward, copy, print, or download this email. Right? Great for lawyers, it would seem. Great for business. Great for private correspondence. But why is this perhaps a bit misleading? Like, where should the skepticism come from here? Even a company like Google, I dare say, they've probably buried the caveats that I'm hinting at under the learn more. But unfortunately, that might be too late. Yeah, in back. Yeah, I mean, those of you who know how to take a screenshot, that's the simplest way. If you don't know how to do that, well, here's a phone. I can just take a picture of what it is I see on the screen. And so these are software defenses that are in place that essentially disable the forward button, disable the print button. But honestly, as you probably already know, once something is already digital, I mean, it's out there. And there are other ways to get at it. It might not be as high quality if you're taking out your phone to do it. But you should view things like this with skepticism. And even when I occasionally receive something like this, I kind of roll my eyes, but regret that the user thinks what they're doing is consistent with this language, but it isn't necessarily. And so indeed, in part, from an introduction to computer science, you begin to, get a little scared from what's going on out there, because there's so many different threats and so many things that you can't, in fact, do. And the onus is unfortunately often on us users to read between the lines and see what actually is possible. Here's another one that you might be more in the habit of using. Incognito mode or private mode in Chrome or Safari or Firefox or Edge or the like. What does incognito mode do, if familiar? What's incognito mode? Yeah. It doesn't log locally what you're doing. Exactly. Most people here probably generally know about things called cookies, even if you're not quite sure how they work. But they're like these little remnants or breadcrumbs you leave behind when visiting websites that allow the websites to keep track of who you are in some sense. According to Google here, when you're using incognito mode, Chrome won't save your browsing history. So that's good. Cookies and site data, information entered into forms. But to their credit, they do disclaim that your activity might still be visible to the websites you visit, your employer or school, your internet service provider. So they're getting better at least helping you evaluate by giving more of the facts whether you do or don't want to do this. But this doesn't mean that the websites you're visiting indeed know don't know who you are. All of our computers have unique addresses, these things called IP addresses that you might have heard about. In CS50, we'll explore these in another week's time. Your computer is constantly leaking information that could be used to infer who you were. So this is really just best left when you don't want to accidentally, unlike a friend's computer or a lab computer, remain logged in, because cookies are typically used to just remember that you've logged in. So if you use a friend's computer, you use incognito mode and just close the window, boom, you're effectively logged out. But even as Google disclaims, there's other caveats there too. So what else might we keep in mind? How about, let's consider one other big one that's another thing to start looking for increasingly in order to keep yourself secure. And this one's a little more technical, encryption. And as CS50 students will know, this is something you can implement in code. And in fact, let me ask this question. What does it mean to encrypt something? Think back to PSET 2 and Caesar and the like. Let me look a little farther back. Almost any student hand should theoretically be up here. Yeah. Exactly. Encryption is all about substituting one letter for another and generally scrambling the appearance of some message up so that the recipient knows how to reverse that process and see what you actually sent. But anyone intervening in between you can't actually see the information between you. So just to impress the parents in the room, any students, what does this say? We're not ending here, but this was CS50. That's what it would say. But notice the scramble. Let me go back and forth, back and forth. In this message, T becomes you. H becomes I becomes J. S becomes T. This is what we called a few weeks ago in CS50 a rotational cipher, a Caesar cipher that literally does, as you described, substitutes one letter for the next. But it does so in a very predictable way. A becomes B, B becomes C, and so forth. And we also talked weeks ago that you don't have to keep it that simplistic. You can use a bigger mathematical formula to make it at least harder for some adversary to figure out. But you and I, as users these days, are constantly, thankfully, using encryption. You probably generally know that you should be hoping for, expecting this these days. Like HTTPS is a good thing. S means secure, literally. And any website that has that in its URL indicates to you that you and the website are having an encrypted, a scrambled communication, which means if you type in your password, your credit card information, anything else personally, no one between you, theoretically, points A and B, should be able to know what it is you've typed into that web page. The web page absolutely can, because they have the ability to decrypt that information, to reverse the process. But at least encryption is generally a good thing. But today, let's take that one step further and encourage you all to be looking for, expecting, if you will, as consumers increasingly in the coming years, something better than encryption alone, but end-to-end encryption. And you're starting to read about this a little bit more, but it's perhaps a little less familiar. Someone in the room who's familiar, what is end-to-end encryption? Let me give folks a moment. What is end-to-end encryption? OK, yeah.
It's where you always try to when encrypts a message on one side and sends it where it's encrypted.
Good. So it's when an app like WhatsApp encrypts a message, but it's encrypted all the way to the other side, to the recipient, even though Facebook, in this case, owns WhatsApp, even though your message is going through Facebook or Meta's servers, they do not have, theoretically, the ability to decrypt your message, whatever chat message you've sent to a friend. They are just sending seemingly random zeros and ones all the way to the end user, who can then decrypt it. If you're an iPhone user, iMessage, for instance, does this automatically, so long as your text messages are blue and not green. That means you're using iMessage and Apple's platform that does this. But let's focus perhaps on something that's been all too familiar to most of us over this past year, Zoom. Right? Zoom actually took some flack some months ago because in their marketing literature, they were advertising end-to-end encryption. They were not implementing end-to-end encryption, at least initially. This was probably marketing gone awry, not quite understanding what end-to-end encryption means. They were using encryption. And what that meant is that if I were having a meeting with a colleague or you were sitting in on a class with a teacher, you might have an encrypted connection, all of you, to Zoom centrally. But they had the ability early on, and still now if you leave this feature off, to decrypt that information and see and listen to, theoretically, anything going on in that meeting or that classroom. Now, technologically, there's not really a good defense against that if using that older approach. All it really is policy, where hopefully there's rules in place, there's contracts in place that say, well, yeah, that's possible, but don't do that. End-to-end encryption is a stronger guarantee for you that circumvents that risk altogether by ensuring that if you're tuning into that class or you're logging into that meeting, all of the zeros and ones are going through Zoom servers, just like Facebook's, but only the end users, only the students and teachers, only the colleague and colleague can actually decrypt and see and hear what it is that's being said. And if you're one who schedules Zoom meetings, you can actually see this. For instance, here's a screenshot I took yesterday too, scheduling like a Zoom meeting for today. And you'll see that you can choose the day and the time, the password, haha, and also down here, the encryption level. And by default, it's typically enhanced encryption, which is stupid, like enhanced encryption. It's just encryption. And in fact, it's sort of worse encryption than the other checkbox, which is end-to-end encryption. But there's this little caveat. And here, too, consistent with this reality in computing, there's always a trade-off, right? It's not all upside and all win. Several features will be automatically disabled when using end-to-end encryption, including cloud recording and some phone stuff. I mean, that's already kind of a big loss for a class, for instance, a conference that wants to keep the sessions. But it kind of makes sense, right? If the data is encrypted between all of the end users, and therefore Zoom has no eyes into the data or ears, then it makes sense that they can't record it for you in the cloud because it's completely scrambled to them too. So a good primitive to have in place, but also something that you need to sacrifice in terms of usability. Well, let me, in our final moments here, let me flip back over to where our hacking tool is. It would seem that 8 characters is doing really well because we still got 3 A's at the beginning of this. So that might be, in fact, one takeaway. And in fact, let me flip over and propose 3 pieces of homework for everyone here. 1, use a password manager, the one that's built into your phone or your operating system, or pay a little something more for something that you might like a little better. 2, use 2-factor authentication for more of your accounts. Maybe not all, but at least more of your accounts. And that's certainly a net improvement. And then 3, use not just encryption, but end-to-end encryption. And unfortunately, these features are not all quite as simple as, oh, well, let me just check the box and turn on that something that's always been available to me, because it's not always been available. And Zoom, only once they sort of got into trouble for this did they acquire some other company that implements this feature and then add it to their software. But as users, as consumers, as parents, as students, considering choosing one tool or another because of these features is really something you are empowered to do. And to not use those tools that you don't think meet some threshold of comfort for you. For more on this and computer science more generally, any of you can take CS50 online at edx.org/CS50. It's been so nice to see you. Happy to chat one-on-one, but otherwise have a wonderful day here on campus. This was CS50.